Hello, we're now talking about Chapter 7, Sections 7.1 through 7.4 in particular. This chapter is still about statistics, so it's still part of Module 5. The difference is in the type of question we're going to be asking. In Chapters 5 and 6, when we talked about statistics, the issue was, here's some data, somehow it was obtained. What can we say about it? And so we made graphs, we computed averages, measures of spread, and so on. In Chapter 7, the situation is, okay, here's a scenario we'd like to study, a question that we'd like to answer. How can we get data in order to begin to analyze it? Where does the data come from to begin with? So, for example, how would you estimate the percentage of adult Americans who own a cell phone? I suppose one way to conceptually answer the question would be to literally go around and follow every adult American for a bit and watch carefully to see if he or she used a cell phone. You could ask them, but they may not tell the truth. And that's ridiculous. There are probably 200 million adult Americans, something like that. It's impossible to do. Or how would you estimate the percentage of adult American cell phone users who pretend to use their cell phone in order to avoid social interaction? Maybe I could ask how many of you have done that. So you're sitting beside someone and they look a little shady, and so you pretend to be texting so you don't have to talk to them. This is an even harder question, I think, than the first one, because now people tend not to be very honest when they're answering questions like this. Or 3, how would you estimate the mean number of text messages exchanged per day by 18 to 24-year-olds? That might be the easiest of the 3 questions, but if we're talking about all Americans, it's just unthinkable to actually talk to everyone. And so what you normally do in situations like this is look at a sample. So the population, a statistical term, by definition is all the data of interest, whereas the sample is a subgroup of that we choose for study. And then how this sample is chosen is the topic of today's lesson mainly. How do you choose good samples? Here's an example. At the end of its first year in business, a new restaurant wants to know how it's been doing with its customers over the past year. For 1 week, surveys are placed on each table, urging customers to rate the restaurant. Suppose 1,000 people eat at the restaurant that week, and 50 surveys are turned in. What's the population? What's the sample? By definition, the population is all data of interest. This restaurant has been in business for a year, and each of those people who came during that year was a paying customer, and presumably were interested in the opinions of all our paying customers. So all patrons of the restaurant during the past year. What's the sample? The sample is the data that you actually managed to collect in order to study. We only had 50 surveys turned in. So 50 people who turned in the surveys. And what's the 1,000? Well, that's kind of an intermediate group. The 1,000 is part of the population, and the sample is part of the 1,000. Another example. Suppose a sample of 100 female and 100 male IWU students was taken. The average GPA of the females was 3.2. The average GPA of the males was 3.1. Do we know that these women have a higher GPA than these men? By these women and these men, I'm talking about the 100 women and 100 men who were studied. Answer: yes. This is not a matter of interpretation. as long as we didn't make an outright blunder, and we'll assume not. All we did was compute a mean. There's nothing ambiguous about that. Do we know that, question number 2, do we know that IWU women overall have a higher GPA than IWU men? No, not necessarily. How do we know that these 100 females who were selected are completely representative of all of the women at IWU, and likewise for the men? So this points out an issue already with sampling. It introduces the possibility of making errors, not computational kinds of errors, but errors due to misrepresentation of the data, that somehow our sample would not accurately reflect the population, and then the conclusions that we draw from it might not be completely correct. So this example is an illustration of the difference between population and sample, and this then points out an example of analyzing the sample, and that's an easy job, there's no question about that, versus analyzing the population, and that becomes a much dicier business. There is potential for error there. Descriptive statistics means factually analyzing the data gathered. That would be like computing the means of the 100 men and 100 women in the previous example. Inferential statistics means using the sample to make a claim about the population. That would be like saying, because of our data on the 100 men and 100 women we gathered, we're going to conclude that the GPA at IWU of women is higher than that of men. That's inferential statistics. Let's now talk about types of sampling. There are a number of different types, and I'm going to mainly discuss the two extremes, convenient sampling and simple random sampling. In convenient sampling, we do just that. We use the most convenient sample available. So when I teach this course in an on-campus setting, I give away lots of money in class. Sorry about that. It's kind of hard to do that online. So maybe you want to see how students will react when you give them a $100 bill. And so convenient sampling would be I'm in the front of the room and I just walk to the first 3 people in the front row and give them a $100 bill. Whereas in random sampling, we do some sort of careful procedure to ensure that all possible samples of the same size are equally likely to be chosen. So if I'm going to give away 3 $100 bills in my MAT-107 class, I could put everybody's name on a slip of paper, put all those slips in a box, shake them up, and draw out 3 names. And then any group of 3 people are equally likely to be chosen as any other group of 3 people. Random sampling is usually better than convenient sampling, and we'll talk about some reasons why in just a moment. How could we get a random sample of 4 of Snow White's dwarves, IWU students, citizens of Marion, or U.S. citizens? Let's briefly take them one at a time. Of Snow White's dwarves, well, there are only 7, so put their names on a slip of paper, draw out 4, as we said earlier. IWU students, okay, now there are about 3,000. So writing them on slips of paper and shaking the papers up starts to become something I probably don't want to do. On the other hand, computers are very good at things like that. So it's not too hard to get an electronic list, say an Excel spreadsheet of all IWU students, and then you can have the computer randomly choose 4 of those names. Citizens of Marion, it's getting harder. Now we're talking maybe 30,000 people or so. And it really isn't anybody's job to maintain a list of those 30,000 people, even in electronic format. The closest thing you might be able to do is the phone book, but not everybody is in the phone book. For example, college students tend not to be in the Marion phone book, even though you're citizens of Marion while you live on campus. And homeless people aren't in the phone book, and other people don't have listed phone numbers too. United States citizens. Now it's getting really tough. Out of 300 million U.S. citizens, I want to pick 4 of them in a way that every group of 4 people is equally likely to be chosen as every other group of 4 people. That's impossible to do, actually. There's just no list of the 300 million people from which I can randomly select. And so this points out why, even though random sampling is good, it's not used all that often, at least not in its purest form that we talked about. So in practice, a sampling method is probably going to be some sort of combination of convenient sampling and random sampling. We mentioned that when you do sampling and look at a sample in particular, there is potential for making mistakes. So we'll talk about errors in the context that the results from the sample don't follow the results from the population. Maybe we sample some IWU students and look at their GPAs, but in the background what might be happening is those GPAs don't match very well the overall GPAs. Errors can be classified in 2 broad categories. One is bias and the other is sampling error. So think about bias. It sounds bad. It is bad. If you've ever driven a car that's out of alignment and so the tires are imbalanced, and when you drive a while, the wear on the tires is uneven. But more pertinent, when you're driving a car that's out of alignment, you have to keep your hands on the steering wheel because otherwise it'll veer to the left or veer to the right, and always in the same direction if it really is out of alignment. If you take your hands off the wheel and it's out of alignment one direction, then it'll always say veer toward the side ditch. In statistics, sampling in particular, bias is a skewing of the results always in the same direction due to improper sampling technique. We're doing something wrong and it's consistently swinging the results too high or too low. On the other hand, sampling error is a more random type of error, and it's introduced just by the very act of sampling. If you sample and only look at the sample, you're not looking at all of the data, and so it's almost unavoidable that some error will be made. Hopefully that error will be random. So this would be like the scenario where the car is in alignment. You take your hands off the wheel and it might veer to the left, it might veer to the right. Next time you take your hands off the wheel, it might veer to the left, it might veer to the right. But it's not this constant dragging you off to one side like bias is. So sampling error is not considered as bad as bias. So when we do sampling, we want to think about these types of errors as we construct our sampling method. And we're going to seek actually to minimize bias, whereas we're going to try to eliminate bias, whereas we'll only try to minimize sampling error. So bias comes in many different ways. Let's look at 3 different types of bias and how they might come about and what you might do to get rid of them. Then we'll talk about sampling error. Let's do that by looking at a series of examples. To determine the average household income of Indiana residents, suppose I randomly choose shoppers at downtown Indianapolis shopping malls. Okay, what's going to happen if I do that? I'm in Indianapolis. I'm at a mall. If you know anything about Indiana and Indianapolis in particular, you know that average household income in the Indianapolis metropolitan area is probably higher than, well, it certainly is higher than the average in most of the rest of the parts of the state. And furthermore, a shopping mall, though it's not, it doesn't turn people away, it does tend to attract people with higher incomes than the overall average. I mean, other people might tend to go to department stores, discount stores, secondhand stores, and so on. You probably are going to find wealthier people at shopping malls than on average. So coupled with the Indianapolis factor, Indianapolis mall shoppers are probably wealthier on average than all state residents. This is an example of selection bias. The way that we're contacting people and getting them into the sample so that we can collect data on them is biased. Wealthier people are more likely to get into the sample than lower economic status people. And that, of course, is going to have a bad effect on my desire to accurately estimate average income. So another example. To determine how Marion residents feel about the mayor's performance, numbers are randomly selected from WXYZ pages, last names, of the Marion telephone directory. Is this okay? It looks better. I mean, aren't we selecting randomly, at least from part of the telephone directory? Why should your last name, the starting letter of your last name, have any bearing on what you think about the mayor? Maybe it does, maybe it doesn't, but I will tell you that these letters tend to be the starting letters of the last names of Asian people more than other ethnic groups in the United States. So this method will tend to collect more Asian residents than they proportionally actually are. A higher percentage of the sample will be Asians than of the Marion population. Now, is that bad? Well, I don't know. Whether Asians who might tend to be immigrants or children of direct immigrants have a different opinion about the Marion mayor than other residents may or may not be the case. But it is something to think about, and it points out that selection bias can actually tend to be fairly subtle. Here's an example. Should the government take away the constitutional right of the people to keep and bear arms by banning handguns? Randomly selected individuals. We could get into that, but we don't have any information. Let's assume that the selection procedure was random, and so selection bias is not expected to be an issue here. But measurement bias, non-response bias, let's think about that. How about these words, constitutional right of the people to keep and bear arms, banning, government, take away. Nobody wants the government to be taking away our rights, and keep and bear arms is directly from the Bill of Rights, one of the amendments to the Constitution. This is an example of measurement bias. The question itself influences people's opinion on the issue. This is a question that might be asked by, for example, the National Rifle Association, which is a lobby group designed to keep the government from passing laws to do just that, to put restrictions on gun ownership. And so they might ask this kind of question, hoping that the question itself will encourage people to say, no, the government shouldn't take away these rights. So wording of the question influences, at least potentially, the response. Again, this is measurement bias. Examples 1 and 2 were selection bias. This is measurement bias. Or how about this? To determine the prevalence of crime in a small neighborhood, police officers conduct a door-to-door survey of each house in the neighborhood, asking them if they know of any neighbors who have been crime victims. I don't know if this has ever happened to you, but knock on the door. You're at home. Knock on the door. You go to the door. There's a policeman there, and he has some question about, do you know if the neighbor's house next door has ever been broken into? Well, even if you're totally innocent, and I hope you are, that might send your heart rate up a little bit. Here's a policeman, and he's checking what I know. Apparently there's been a crime committed. Perhaps there's been a crime committed in the neighborhood. I'd really rather not get involved. You know how it goes. So people may tend to deny knowledge because they don't want to get involved. If I say yes, then he's going to start asking details. This is another example of measurement bias. It's not the question itself so much as the measure of asking, the method of asking the question. You have a policeman on the doorstep asking you the question. There's nowhere to hide. There's no privacy. This is a policeman. It's just not a good way of taking a survey. A phone survey is done in which respondents are asked if they have ever used illegal drugs. Okay, this is problematic. I hope you agree. It's a phone survey. I'm sitting at home, the phone rings, I answer it. The questioner, the person says, I'm doing a survey. Could you tell me if you've ever done heroin or marijuana or something? Why should I tell you? You obviously know who I am. You just called me. How do I know that you're not the sheriff, the police officer in the previous example? Just checking to make sure that I'm not dumb enough to confess to something. So another example of measurement bias. If you really want accurate results, this would be a very difficult question to get accurate results, by the way, because people tend not to tell the truth. If you do want accurate results, you're going to have to do the question in some way that preserves people's anonymity, that helps keep them anonymous, probably through a written questionnaire. Or how about this? Ann Landers, a newspaper columnist, advised her readers who had children to write in telling her whether they would have children again if given the choice, and 70% said they would not. This actually happened about 20 years ago, and it was made national news. It's like, oh my goodness, American parents are miserable. Most of them would never have their kids again if they had the chance. But think about it. Not everybody reads Ann Landers. She's an advice columnist, was an advice columnist. So people who are reading her column may be people who are already a little bit desperate and need all the help they can get. And more importantly, people who choose to write in do so because they have an opinion on the subject. The vast majority of people presumably read the column and said, oh, that's interesting, and never did anything about it. And so here's an example of a situation where we only get opinions from those who feel strongly about the issue. It's an example of non-response bias. Each person got to choose, who was contacted, got to choose whether they responded or not, and then people who bothered to respond may have a different opinion on the issue than people who chose not to respond. It's an example of non-response bias, and to give you an idea of how badly this can skew the results, after this 70% number came out, another company, a polling company, scientifically designed a good study and found that the actual percentage is more like 9% of parents would not have their kids again if given the choice. So that's still too bad for those 9%, but that's a lot different than 70% of the parents. To determine the satisfaction of people eating in Baldwin, I approach people in the lunch line and ask them to take my short survey. Maybe you've even done this in a class or some other situation. It sounds not too bad, but this is another example of non-response bias. People have the option of answering your survey or not. And those who do may have a strong opinion about Baldwin, and so they may be more inclined to answer because they think Baldwin's food is really bad, or perhaps that it's really good. It's also an example of selection bias. I approach people in the lunch line at Baldwin and ask them what they think of Baldwin. If they think it's really bad, they're not probably going to be in the line to begin with. So this has several problems. All right, to summarize, selection bias. The sampling method excludes a subgroup of the population in a consistent way. So if we're talking about sampling Marion residents, for example, that's our population, and we decide to choose from the phone book those whose numbers are in the phone book become what's called our accessible population, and the sample then becomes those who am I actually able to call. How do I reduce or eliminate selection bias? I need to make sure that the accessible population is as much of the entire population as possible. If so, then the selection bias problem goes away. But if the accessible population is not all of the population, then there can be people out here who have an opinion about the subject and they don't have a chance of making it into the sample. And now I have a non-random effect going on that can skew my results. In measurement bias, the question itself or the way it's asked influences the response. So, example of the worded question about the government banning handguns and so on. So, if you're doing a survey, you better be careful that the question itself doesn't lead those who are taking it. You have to design the survey with regard to the wording of the questions, the behavior of the person asking the questions, whether the people taking the survey have anonymity or not, and so on. This problem of measurement bias through questionnaires has been studied, and believe it or not, the gender of the questioner, those who are asking the question, their physical appearance, the time of day, and so on, all of those things can help influence people's answers, and they're all examples of why the survey would probably be plagued with measurement bias. Non-response bias, a subgroup of the population chooses not to respond. You should avoid this situation. So if you're giving a survey, you should try to give it in some way in which the respondents are required to answer. So, or at least strongly encouraged to answer. So that's why most surveys that you see online, if you take it, you have the option to be entered into a drawing to win a prize. They're trying to encourage as many people to take the survey as possible, partly just because they want to get data, but also partly to try and overcome this problem of non-response bias, where you only get strong opinions. Sampling error, then, is the other kind of error in contrast to bias. For example, if I were in the classroom on the Marion campus and I had 25 people in MAT-107 and I decided that I wanted to take a sample of 5 people in order to estimate the average weight of the people, of all the people in the room. Well, all the people in the room, all 25 people in the room have an average weight. That's a specific number. Now, mathematically, it's almost certain that no 5 people in the room by themselves have an average weight that's exactly the same as the overall classroom average weight. It's just not mathematically likely to happen. And so no matter which sample of 5 people you take, you're still going to get an incorrect result. Hopefully not badly incorrect, but somewhat incorrect. That's sampling error, and because you can't avoid it, what you do instead is try to minimize it, make it as small as you can. The only thing I really want to say about sampling error is that the way to control it is with the sample size. In fact, though we won't go into it, there's a mathematical relationship that tells you if you want results, for example, that are accurate to within 4 to 6%, then you need a random sample of size 400. If you want more accurate results, accurate to within 3 to 4%, then you have to gather a bigger sample, 750, and so on. In a election year, this is 2012, so we'll be seeing it this fall, various organizations like Gallup run polls of, publish the results of polls of how people plan to vote and try to predict the result of the election. Quite often, they are trying to do a national sample, and even though there are 300 million adult Americans, typically those Gallup polls that I was mentioning only involve perhaps 2, 3, 4,000 people. So if you do the sampling well, then no matter how big the population is, here's a relationship that shows about what your margin of error is going to be for a given sample size. It's not the size of the population that's important, it's the size of the sample. Bigger samples are better because they have smaller sampling error. Thanks.